Good morning. My name is Bob Brown. I'm VP of Engineering and Regulatory Affairs at WaterFurnace, and I'm going to be speaking on heat pump sizing and peak demand comparison. Now, in full disclosure, I did do a variation of this presentation at IGSPA here a month or however long ago it's been. But there's some new late-breaking information on some of the cold climate heat pumps. I also put in variable speed product for a better comparison. So there are some significant changes, I guess, from that perspective, but it is generally kind of the same if you did happen to see that. So I'll just start out with a renewed interest in decarb and ultimately the replacement of gas appliances with heat pumps. Our industry is once again very interested in peak demand. Most of the current emphasis is on cooling peak demand because most of the utilities are summer peaking. But actually, when I got into the business here, especially Niagara Mohawk up in this area, they were all winter peaking. And so, of course, things kind of flipped to cooling, summer peaking. And so now we're back to everything looking toward probably switching back to winter peaking, at least at some point. The prediction is here in a couple of years. So decarb and winter peaking utilities will put the spotlight on sizing the heat pumps for heating and the choice for auxiliary supplemental. All of those kind of things are going to be super important in the future. I can't really talk about peak demand unless you really start talking about the sizing of the equipment. And so you'll hear me talk about that a lot in here because traditionally heat pumps haven't really been, especially air source heat pumps, have not been sized for heating. They've been sized for cooling, and then you kind of let whatever happens on the heating side happen. But those are all going to be things of the past, I think, in the future. So what you're looking at here is maybe looks like a complicated chart, but you've got a heat load line here, this red line, and the cooling load line is the blue line over there. And we assume that you start with a 70-degree thermostat set point roughly, and outdoor temperature, then you go from there. And then that's how you actually get your cooling and heating load lines with your heat loss, 50,000 at 70 degrees, for example, here, and 30,000 at 20. But in reality, way back, GE did this study back in 1982. They actually measured the heat loss of a home and put a dot for every hour. So there should be, feel free to count on your own, there should be 8,760 hours on this plot here. And so when they plot the heat loss of the home relative to the outdoor temperature on the x-axis at the bottom, it will actually give you that load line, so to speak. And so you would have expected it to be from 70 degrees on down, but obviously the dots don't quite line up with that. If you've ever done a heat loss or heat gain calculation, you know that most of the time we've used what are called the old degree day method, which was actually based upon 65 degree, and it's a little bit closer, but that was set in the 30s back when heat loss and heat gain calculations first began. Homes weren't insulated very well. They were kind of loose, and so 65 isn't very accurate for today. And so really what is more accurate for today's homes is in the 55 to 57 degree range. So what this is trying to say here is where it crosses the axis there at 55 degrees, that's where you actually need heat in the home. Above 55, you don't really need heat in the home, and that's because of internal gains, solar gains, all of those kind of things wrap up, electric use, all that wraps up into internal gains. And so this is an important part when you're trying to calculate annual energy use, but it's not really a peak, and I'll talk about that probably a little bit later on. So again, going back to our chart there, you can see the red line has been shifted down to about 55, and so we're going to be looking at these load lines a lot today to try and predict when electric heat and all those kind of things are going to come on. And you can see the cooling load line there on the right, the blue line. And so we've adjusted that for those internal gains and electric use, people, solar, all of that is where that comes from. So let's take a look at what a typical heat pump system would look like. Now, this is a ground source heat pump, but an air source would really look very much similar, at least in the way the lines will intersect. So if you can see here, this is a single speed, and so you can see the capacity of the unit based upon the lighter loads is higher, and then it drops down as the outdoor temperature drops down. Typically for ground source heat pump, it's because the loop temperature drops. For an air source, it's because the outdoor temperature is getting colder. But you can see that it hits the load line, and then at the load line, it will probably maintain a temperature. GEO does at least. Air source would keep dropping off. And then, of course, you need to make up this heat here, usually with a supplemental and auxiliary heater. And so that would be called the balance point of the system, and that's really how the heating side is done. On the cooling side, it works pretty much the same way, but you don't have any supplemental cooling typically, so you try and make sure that you've got enough cooling, and typically people will actually like to have a high runtime anyway for dehumidification, so they don't worry about this quite as much, but you do size mostly for cooling for traditional air source heat pumps. GEO, we've traditionally tried to size around the heating side. As we get into higher technology, here's a two-stage equipment, which is more common today. And you can see the part load. So this would be like the low speed or first stage is a much lower capacity. And then, of course, when you hit that line, you're going to start bouncing between first and second stage, and you're going to track with the load until finally you're full 100% of the time you're on high speed. And, of course, then you still have that auxiliary that would need to kick in beyond that point. So finding out how that where that line is at is equally important on a two-stage, but you do track the load a lot more accurately with two-stage equipment. And then we'll see here that as we add the variation of variable speed, of course you can see that it's a much lower capacity. Usually the turn down is at least 4 or 5 times, so you're getting into 20-25% capacity. And you can see that you can do the very same thing and track the load most of the time. This is why variable speed equipment runs a fair amount longer than single speed or dual capacity, is because you're running at a much lower capacity but a lot longer. It typically results in a very comfortable in the home, and also lower RPM also generally means higher efficiency. So variable speed gives you that benefit in there. And then, of course, we still have that balance point up here where we run 100% of the time, and the equipment's doing everything it's got, and you would still need supplemental if there's any operational time in that area. So that's just a quick outline of what these charts look like, because we're going to be looking at those in probably a little bit more complicated way as we go forward here. So let's talk about air source heat pump sizing basics. So historically, air source heat pumps are typically sized for cooling. It's predominantly central to southern product applications. Those in the north, we haven't really had a lot of heat pump applications over the years. Most of the dealers in the north have kind of steered clear. There's usually been natural gas available, so it's obviously the predominant. But I think you're starting to see more and more heat pumps, air source heat pumps, get sold in the north. Historically, most of those have been locked out below 37 degrees. So when you have a defrost, that you got to switch back and forth to try and defrost a unit at those 37 to 25 degrees. Historically, if I still talk to dealers, there's an awful lot of heat pumps that are locked out 37 degrees and below. And what that means is you're really running on electric heat when it's outdoor temperatures below 37. To limit operation and defrost and improve that reliability is really the impetus of that. Electric heat or gas furnace backup has been the heavy lifter for the heating side, with most of that product in cold climates. And that old school practice probably is disappearing more and more, but it's still fairly prevalent. Decarb is relying on these heat pumps for all of the heating. And so some utilities and manufacturers have renewed interest in dual fuel to limit the electric heat use at those cold outdoor temperatures. But obviously that kind of counters the decarb trend, and so there's some There's a little bit of conflict there as to exactly how to handle that. We're going to talk about that quite a bit, quite heavily here. So here's an air source heat pump. So this is a slightly different looking chart, but you can see the load line here is that blue dotted line, the heating load line, and outdoor temperature is here, and the bars represent the hours of operation, and this is actually Albany, New York here, so I've done the presentation here more about a local weather here. So you can see we still have a few hours clear down to minus 18, minus 13, minus 8, but the predominant most of the hours are really above the 12 degree bin temperature there. And the red line is the the heating capacity, the air source heat pump, and the numbers here represent the efficiency of that particular product at that particular temperature. So for instance, 47 is a pretty common temperature for an air source heat pump. That's a measurement point. We have a COP of 3.4. At 17, we got a 2.1. Here we have 1.5 at 5 degrees. And then it essentially goes to a COP of about 1, anything below that particular point there. And so this particular heat pump that's being modeled here is a 16 SEER. Two-stage, and I've not shown it exactly the way a two-stage for clarity, but if you recall, you'll have a part load and a full load, but it was going to get a little messy in the slide, so I kind of kept it like it's on full load because we're not really analyzing the operational costs here, but more how it handles low temperature. So you can see if you size for cooling, you have a fairly high balance point here of maybe 22 degrees, and so you've got electric heat required in this triangle. Now there's not a lot of hours down here, but from a utility perspective, having electric heat turn on is a demand that is a problem from the generation standpoint, and so that is really something we're going to try and take a look at. I do have the defrost zone here, so from 37 to 25. Roughly in this zone in here is where you're going to be running defrost. So if you shut the equipment off, essentially all of this area is electric heat, or if you're dual fuel, it's going to be a furnace backup. So you've got a lot of hours in that area that you're going to have to make up. And that's, as I said, that's kind of the old school way of doing it, and probably disappearing to a certain extent, but I think there's still a lot of systems out there that do that. So again, an air source heat pump sizing for cooling typically results in this balance point being fairly high. And so that's kind of summarizes a basic air source heat pump. We'll kind of come back to all of that with the cold climate heat pump as well. Now, switching over to the ground source heat pump, historical sizing for ground source heat pumps, when I first got in the business, we were trying to limit first cost. And so if you look at that, you typically would size the heating for a balance point really just below the significant bins of a lot of hours, right? Because you're going to limit the size of the equipment to a certain extent, maybe trim a ton off the equipment, a ton off the loop, your first costs are lower. So you can still retain good cooling dehumidification with a slightly smaller unit, and back when we were selling single speed equipment a lot, that was important, and so that all made sense back then. Minimal backup heat, it was typically less than 10% of the total heating bill, so it really wasn't a big deal. Sometimes it's $20 or $40 a year to offset a whole loop ton and a whole loop ton or a whole ton of equipment, and that could be $5,000. So your payback wasn't there to really put in the big equipment. So it was the economical sizing, and that's the way we did it for a long time. Full heating sizing came about primarily in the mid-90s when a lot of the rural electrics were worried about peak demand more, and they had a fairly substantial rebate. You could get $1,000 or $2,000 sometimes per ton even, and if you did that, then they wanted you to have a piece of equipment that did not require what I'm going to term auxiliary heat, that is electric heat that would turn on with the heat pump to do that supplemental little triangle on the top. And in order to do that, you had to size equipment slightly bigger to get that balance point down there low. And of course, those rural electrics have done that really for 20 plus years now, and so that's very common. This will probably be the norm, as my bullet there on the bottom. This will probably be the norm for all future ground source heat pumps, is to really do that full sizing, because that peak demand issue, as we talk about the healthiness of the grid, that is an important thing. So let's take a look at a ground source heat pump, and I've got multiple sizes on here so you can kind of see the effect of that. You can see the load line of the structure is the same right here. So there's the house load. We've got the Albany, New York hours here, and I've still got the 47, 17, and 5 vertical lines there so you can kind of see where that's at. But I've got the COPs written up here for a ground source heat pump, and this is a variable speed unit. So you got COP of 4.8 up here at 47. Now this is outdoor air temperature, and so there's a corresponding loop temperature. The corresponding loop temperature, but I didn't bother to put the loop temperatures on here. But this is a typical loop profile of, I think we hit minimum of 32 down here, and it probably goes up to 56 maybe at the super part load. So your loop temperature's ranging in there. So you've got a 4.8 here, 4.2 at 17, and we've got 3.8 COP down at 5. And then, of course, it stays solid all the way through here, because once you hit 100% runtime, your loop was sized for that particular operation, and so you really just keep humming along at that same performance, no matter what the outdoor temperature is. So we maintain that 3.8 all the way through that, and so that's really a good thing. So kind of the old sizing would have been maybe more like here, where you have a balance point in the 5 to 10 degree range, and then you would have had a little bit of electric heat that would come on in this area. But I think more normally now is to try and maybe get up here with a 4-ton, where you'd have a balance point that would be way down here, where you're not going to have any auxiliary heat come on at all. So that's probably more normal for what the sizing is going on today, and so that'll result in only the heat pump actually contributing to that peak demand down there. So now there's a new air source heat pump design for cold climates, and it's called the cold climate heat pump. It's been around for a few years, but the technology is a little bit new, and it's a little bit morphing at this particular point in time. It's basically consists of an oversized vapor injected variable speed heat pump, and that vapor injection gives you some benefits when you're doing heavy lift, meaning really cold outdoor temperatures, trying to pull heat out of the air and then put it into the airstream inside the home. That heavy lifting is typically compression ratios over 4. If you want to look at simply, you could just look at the head pressure to suction pressure, and if that ratio is over 4, then you can benefit from vapor injection there. It is a complex compressor speed management, so they're putting in a larger compressor and then limiting the speeds that it will operate based upon the outdoor temperature. So it's a lot more complex than what most of the products on the market today are. And the COPs they're touting now are roughly at a minimum about 1.8 at minus 15, and the COP of the air source heat pump today is like 1 at that particular point. So almost double the COP of there. The new cold climate heat pump regulations are under development, meaning the standards, AHRI 210-240 has been modified here recently. So you're starting to see some more things about the 5-degree temperature is now being measured and certified and that sort of thing. And then there's also a new standard that's going to replace 210-240. I'll go into that here, I guess, in a second. That will be more heavily into the cold climate heat pump. Early on, I think the important thing is early on there were some lofty claims from the cold climate heat pump, but most of those are starting to disappear with the changes in the standard where we're actually getting certification on some of those points. So what happened was DOE in 2021 launched a cold climate heat pump challenge, and they put a specification out. These are some of the requirements they put in for that specification. Minimum 47 degree capacity had to be, so they weren't playing some games with that kind of thing. They had some minimum capacities specified. They had the heating capacity at 5 degree had to be greater than 70% of the 47 degree. Hence, the variable speed management is kind of keeping track of what compressor speed it's running at based upon outdoor temperature. Minimum COP at 5 needed to be at least 1.8. Minimum of 8.5 HSPF2 for region 5 using the new M1 appendix. I'll kind of go through most of the other stuff you can probably read there. Essentially a low GWP refrigerant in 2021. Obviously, we were looking toward the new refrigerant, so they had to include all of that. So that was in that challenge, and most of the manufacturers, the big manufacturers, took that challenge up. Those units were installed and monitored, and some of those reports are available, and some of them are still happening today. So now we're going to put all the product together on one chart, and we're going to kind of look at the results of the peak demand here. So we've got air source heat pump. I've got a 4-ton 2-stage 16 SEER 2 with electric heat, a cold climate heat pump 4-ton. New market, I've got some new market data that came out that I'm able to actually see actual performance data of the cold climate heat pump, and then of course a ground source heat pump variable speed that I'll show you here that roughly is a 40 EER 5 COP from our standard with that. So a little bit more complicated chart, but let's just walk through it. So we've got an air source heat pump as a solid line here. And we've got another air source heat pump. I've got a 4-ton and a 3-ton shown for a traditional 2-stage air source heat pump. The reason I've got these two here is because the 3-ton is probably more what would get installed, but again, that's sizing for cooling, not worried about the heating side. But in reality, going forward, you're probably going to have to install a 4-ton to try and drop that balance point down here to at least get it down into the 15 to 17 degree range. But you still have this resulting triangle to fill in with hours and with electric heat or dual fuel if you got a gas backup. So even moving it from here to there, the benefit is you're taking a lot of hours out of the auxiliary heat, but it's still got a lot of hours happening there. Here is the cold climate heat pump, which is the green line, I guess, as it shows there. And you can kind of see the capacity and the efficiencies at the different points for the cold climate heat pump here. And so as you recall, the 5 degrees is an important point now with the AHRI 210, 240. And so you can see here that you almost are running 100% of the time here and able to handle the full load at 5 degrees. But any temperature below 5 degrees, it's going to fall off quickly because this is running essentially at full capacity, highest RPM. And so any temperature fall off here is due to the outdoor air temperature and the inability to really heat with really cold temperatures. You can see the line fall there. And so you run a COP down here, even though the COP is really relatively high, you're not getting a lot of capacity out of it because of the air temperature. So this triangle here would still need to be made up by some sort of auxiliary heat system, either electric or gas. And so even though it's smaller and you can see that the COP is a improvement, you still, anytime you've got any hours down here, you're either going to shut the heat pump off shut the auxiliary heat off, which is going to make the occupant uncomfortable, for that period of time, or you've got to do something or use gas or something else if you want to keep it off the grid. So it is something that's going to have to be dealt with, even though there's not a lot of hours there from a utility perspective. They don't really care how many hours. All that's got to happen is once, and that hits their peaks. So now we're going to add the combined. So I got the ground source heat pump added in here, and so this is the orange line for that variable speed ground source heat pump. And you can see one of the benefits of the ground source heat pump is that once you hit full runtime in this area here, we can actually maintain that very high efficiency of 3.8 all the way through there. And so the result is that there is no auxiliary heat really necessary for the ground source heat pump. So the only demand, peak demand, is really just the refrigeration component itself, where if you measured peak demand here for the cold climate heat pump, you would have to add in whatever you're putting in for your auxiliary, which would be most likely electric, but it could be natural gas depending on how you've got your system configured. So that really is the result there of, high COPs can be good, but you've also got to look at the capacity of the equipment for that COP. So quick talk about the standards, and then I'll get into the actual numbers for the cold climate heat pump and the GEO system. So the standards are changing, and we decided during A2L conversion that, hey, let's just change all of our standards too. Makes perfect sense. So 210, 240 is not only been changing, but it's going to be moving to a new standard, 1600. And 210, 240, if you're not familiar, that's the SEER 2 and HSPF 2. That's where that comes out of. And it's going to be moving to a new standard, and they're trying to get that through the DOE right now. And of course, with all the changes in Washington, that's a little up in the air as to whether or not 1600 will actually be adopted here. But the cold climate heat pump is a lot more defined in 1600, so there's some good things out of that that'll help regulate the market with that. AHRI 1600 has a COP peak defined, and so that's a system peak. So if we go back to this slide here, it actually defines that in heating and cooling. And so at 5 degrees, it's defining that peak as the whole system. And so if you sized here, it would really just be the equipment itself. But if you actually picked this temperature down here, you would have to add in the COP of the electric heat in there as well. So it really depends on where that's done at. But at least there's an effort there to try and put some sort of a peak COP in both heating and cooling into the standard. The ground source heat pump, ISO AHRI 13256 is our current standard. We, as you may or may not know, we switched over to AHRI 600 with the requirements from the Department of Energy, but we have not fully switched over with that yet either. We're essentially in the same position as the air source with 1600, so we're kind of half pregnant, if you decide, if you want to say it that way. So the standard is developed, but the Department of Energy hasn't come back with all of our requirements for minimum efficiency and that sort of thing with it. 600 currently has mostly, it's the commercial standard for right now, and we're writing the residential with that. It is planned to include a peak demand, so we're going to be putting that into our 600 standard to try and help all the heat pumps to have some sort of a peak demand that's certified and regulated through AHRI. And the DOE final rulemaking is also in limbo with that particular one. Now, if you're familiar with 210, 240 and how a SEER is calculated, you don't need to see these numbers, but I'm just showing you the spreadsheet so you kind of get a feel for it. If you run a test, like this is a cooling test here, or a heating test, sorry, here. So you would run your heating tests at like several points, and then you plug them in, and the bin method here for the DOE Region 4 is typically what it used to be, will actually calculate your SEER and HSPF, right? You're probably used to, maybe most of you have seen that kind of calculation. This is typically done by the manufacturer and is not released, so you really don't know what these numbers are as a consumer. And so that's where some of the magic happens in here, is if you don't know what those numbers are to plug into this spreadsheet. But the result is a HSPF or a SEER. Now it's HSPF 2 and a SEER 2. And with the new standard, 1600, it's going to change to a new metric called SHORE for seasonal heating. And it's also got off cycle in there. That's what the O is for. And so SHORE is heating and SCORE is the cooling number. And so you got new metrics coming in there as well. So that particular standard, that's the way it's going to work. And we're modeling our ground source heat pump standard after this same kind of methodology. So hopefully at some point we'll be able to actually do a better comparison job between air source and water source geothermal. And so if you get into here, you'll see that this is an outdoor air temperature. And if you look at 5 degrees, the bin will actually tell us how much electric heat we're using, how much current the equipment itself is running. And so you can actually get down at the bottom here, the peak demand at 5 degrees will actually come right out of the chart. And so that's where that will be able to be published, and that'll be useful for the utilities, I'm sure, at that particular point to have a certified data at that particular point. And I won't bore you with the second one. So now let's get into the actual demand. You saw the charts and all that, but I didn't have any numbers on that. So peak demand can be measured really at several points. It's been chosen to hit 5 degrees outdoor, which is not bad, but you know that around here it gets below 5 frequently, and so you'd really like to see something below that. So maybe minus 15 would be a better one, because that's probably more of a worst case scenario. And then of course most utilities are still summer peaking, so you're worried about 95 degrees in the summer. But I will say that the heating, the surprising thing with the heating is they typically have to take the renewable generation out of the heating peak, because the heating peak hits in the middle of the morning, there's no sun, and there's typically not much wind. So they actually have to take those out of the calculation for the utility to give what kind of max power can I generate and put out on the grid. So it is a little bit different, and I think there's a lot of number crunching going on with this right now. But those are the 3 temperatures that we're going to take a look at here in this analysis. The air source heat pump, as I said, is a 2-stage, 4-ton, 16 SEER 2 with electric heat. The cold climate heat pump is a 4-ton with variable speed, vapor injected. And the ground source heat pump is a variable speed 40 EER 5 COP with electric heat. Good. So here's the cooling peak demand, and if you want to take a look at this, you can see that the sorry, I hit a zoom somewhere. Not used to a zoom. Is there a zoom on here? Okay. So here we have on the cooling demand side, so here is the actual peak demand in kW. So you can see that the air source and the cold climate heat pump are very close for the cooling demand. And you would probably expect that at 95 degrees, the vapor injection probably isn't necessarily needed, so that the two are going to act pretty similar with that. But keep in mind, if you don't size for heating, this number could actually be smaller, right? Because the equipment would be probably a ton less in most cases, if not even more than that. And so it's very difficult to look at cooling demand even without knowing how you've sized the equipment. That's why we went through that whole exercise. And of course, here's the ground source heat pump, and we're operating at a much moderate temperature. And then also we have the ability to get a little bit higher efficiencies with water. So you can see that there's a big difference there. Not quite half, but about 60% or so. So if you go down to peak kW per ton, these are the kind of numbers you would see for that. Now I will mention one other thing. a lot of the numbers that get published talk about, in-service units that they're monitoring. And of course, you get dirty coil degradation, that sort of thing, which can tend to make the air source kind of bump up with higher KW for that. And so I did throw in a little bit of slide here because if you take a look and you kind of do a Google search and you look at what we've used in some of our software packages over the years from ASHRAE and whatnot, you find out that a 40% condenser fouling can degrade performance by 16%. There's refrigerant leaking typical, so you're going to have another 12% with that. So there's a lot of issues with an outdoor condensing unit. And what typically you see is that the indoor evaporator doesn't have those same issues because it's inside the house versus, outside where the yard's getting mowed and kids are beating on the condensing unit and that sort of thing. So the beauty of that is that the geothermal won't have as nearly the kind of degradation that you'd have with an air source. ASHRAE has got some down here that after 5 years, that this has been used throughout quite a bit. You see about a 6% reduction after 5 years, which means the KW would actually go up with that 6%. So any number you see from a study, you need to kind of look to see if it's installed units, it's probably got some sort of a degradation in there. So here's the heating side, and heating's a little bit more complicated because I've included auxiliary heat and I've also done it at 2 different temperatures. So let's get set here with 5 degrees, okay? So you can see the first 4 columns are all at 5 degree outdoor temperature. The last 4 columns are all at minus 15 degrees, okay? So let's take a look at the actual heat pump. So here's the heat pump, and you can see the cold climate heat pump versus the air source. Now, is it immediately obvious to you guys why is the cold climate heat pump 5 and the air source 3.44? Anybody want to guess? Well, you got a bigger compressor that's running at a higher speed to give you more capacity, right? So it's over revving, so to speak, comparatively to the air source heat pump. So that's why you see those two diverge here, where on the cooling side you didn't see it. The ground source heat pump is at 2.7 again because the chart, the efficiency, we're able to work at 32 degree entering water temperature instead of minus 15, and there's a pretty good advantage for that temperature there. So here we are with auxiliary heat put in at 5 degrees. And you can see that the air source cold climate heat pump, I should say, just barely has a little bit. If you remember that chart, it essentially was running full capacity at 5 degrees, had very little electric heat. And so that's what you're seeing here is essentially that's full capacity. It was sized for 5 degree balance point. The air source heat pump, on the other hand, went up because it has some auxiliary electric heat coming in, and so it's gone from 3.5 to 6. But 5 degrees really isn't the story because from a utility perspective, you really want to look at 15 because that's what they got to supply, or the customer is going to be uncomfortable, one or the other. And so when you start looking at these numbers out here, now you start seeing how at minus 15, you start seeing the numbers come, expanding here, where now I've got electric heat in both of the air source and the cold climate, and the ground source has got a little bit of electric, but not a lot, right? So you can kind of see the separation of the product there. And then, of course, we've got heat pump COP and total COP when you take into account electric heat and all that. Essentially, the air source heat pump is running at a COP of 1, and with electric heat, it's a COP of 1, so it's kind of a wash. The cold climate heat pump runs at a 1.85 COP, but when you factor in electric heat at minus 15, it's 1.21. So you can see that our equipment, we have just a little bit of electric heat that drops the COP down, but we're essentially 3 times the efficiency at those temperatures. So the benefit from a utility perspective is you don't really want to look at 5 degrees if your minimum really is minus 15. and I'll move on. And so here is kind of a quick summary of the heating peak demand per ton. I've gotten the chart here for heating at 5 and at minus 15. So you can see what those numbers are. Ground source heat pumps roughly at 1. So 3.6 X of what the ground source heat pump is for the air source product. And then a reiteration of the heating peak demands are over here. So, although the cold climate heat pumps are a distinct improvement over the air source heat pump in primarily heating climates, the peak demand is still dominated by the necessary electric heat or gas, depending on how you're going to handle your decarb. And peak demand is prominent at 5 degrees, but much worse at minus 15. So the cold climate heat pump will be forced to operate in the adverse conditions of winter. And I can't say this enough, I don't know that we've got a lot of cold weather experience with air source heat pumps, because most of them have been shut off at 37. And so when it gets really cold out, I don't know that we have a ton of experience as to how they're going to react to that. And we're embarking now with making a lot of air source heat pumps work very hard at those cold temperatures and go in and out of defrost and that sort of thing. So in my opinion, I think that is still largely an unproven environment for most of the historical air source heat pumps. And so ground source heat pumps are still the best solution, I think, to limit that peak demand for winter peaking utilities in the northern climates. And I think you're going to start seeing some of the utilities go winter peaking here pretty quickly, like within a couple of years. So that's really all I've got. So we'll open up for questions. Okay. Yep.
Hey, boss, say what?
Yep.
Stan Marco here from Geosmart Energy. Bob, I was going to give you a hard time early on, but as your presentation progressed, I think you're starting to see the light. So we've been in the geothermal heat pump business for about 40 years, I guess. I'm from Canada. Grew up in a place called Winnipeg. If anybody knows anything about that, it's cold climate. You know, summertime is nice. Wintertime, we get 3 weeks of minus 33 every year. Became the largest contractor selling heat pumps in Canada early on, based out of Winnipeg, selling this product. Okay, so wonderful stuff built by WaterFurnace. And in the prairies in Canada, people are prepared to look at heat pumps and things like that, but it had better work. So undersizing equipment is not an option there. So we have, today we have thousands and thousands of these heat pumps in the prairies in Canada without auxiliary heat. Okay? And in the early years, they said it couldn't be done. And we figured out how to do that. So one is, as Bob said, is sizing. So in 40 years, we have not sold undersized heat pumps. Our corporate philosophy is to satisfy all of the heating in the house with the heat pump. Some heat pumps are sold without any electric heaters in them. And some people think it's a good idea, so we'd be more than happy to sell it to them, because in the end, we make a little bit more money. But the electric heaters that go in our units are programmed in such a way that they don't operate as auxiliary heat. They operate as emergency heat.
Mm.
So in the climates where we get minus 33 as our design temperature, we can run heat pumps, geothermal heat pumps with proper loops at those temperatures for the last 30 or 40 years. No issues whatsoever. The comment that was made is one of the problems in the early years was trying to be competitive and reducing the cost. Most of our customers are spending a fair amount of money to buy a geothermal system. And nobody, certainly not in Canada, nobody goes to buy a spend that kind of money to buy a heat pump that's undersized on purpose. So still today, our philosophy is to heat the whole house, whether it be in Toronto or whether it be in this area, whether it be in Winnipeg or Vancouver or Minnesota. Our heat pumps made by this company for us heat the whole building. We're competitive with all the other competitors, the different brands and stuff. And in the areas that our contractors dominate the area, it forces our competitors to size equally, or they just don't sell anything. So, Bob, there's no issues with the second part of your thing with sizing a little bit. Yes, it's a little bit more expensive, but in the end, that's what people really want. So every once in a while, after 20 years, maybe all of a sudden we'll get a call from somebody and they'll say, I got this peculiar smell coming out of my heat pump. What's going on? Any lights on there? Anything going on? And it'll be the first time that their electric heaters ever come on, because perhaps they had a catastrophic or even just a small failure of the heat pump, and the electric heat came on for the first time in 20 years in a climate that has minus 30-degree weather. So I applaud the direction that you're taking.
And that's why we don't hand out fruit, so you can throw it at me if you're disagreeing.
Tony Gilbert from Pratt. Just a question to Mr. Winnipeg there. So all your stuff is geothermal? Okay. All right, 100%. My real question. So you showed us the, what about on the summer side, right? Because if we're using 50, 60-degree water side, what's the benefit to the grid?
Well, this is the cooling demand. I guess I'm not sure which number you're wanting to take a look at. This is cooling, and this is at 95-degree outdoor air temperature. So our product would be running at a moderate, I think it's high 70s the way this is modeled here. So our loop temperature would be in the high 70s, but the air source heat pump would be working against 95 outdoor air temperature, which is typically our loops would be sized.
Let's set it on the 2 kilowatt, but 3 transistor, and what I can speak up and we would see skip say.
Well, on cooling right there, you've got about 3/10 of a kW per ton. And that's for brand new equipment, yeah.
And so being much.
Yeah.
Okay, I knew it was coming.
Yeah, hi, I'm Hugh Henderson at Owegina Consulting. Good job, Bob, of walking through all this. So the air or cold climate heat pump compared to geothermal comparison, you're seeing that the geothermal demand is about 3 times lower, right? That was kind of your summary for heating.
Talking about heating.
And I understand all that and understand your calcs. So I can tell you from field testing of air source heat pumps, we've seen that ratio be maybe closer to 2. And I think it's because there's diversity in loads. And the other thing, so the 5 degrees versus the minus 15, 5 degrees is closer to what you're supposed to design to according to Manual J, right? It's the 1% condition. And the Clean Heat Program in New York State says that a fully sized system is sized to meet the load at the 1% design condition. But I do agree that the minus 15 happens. It's just that I think there's a couple things that save you, right? One is that maybe temperatures drop in the house a little bit and people may or may not notice. And the other, there's thermal mass in the house. And then the other thing is diversity. If you have electric heat, and I can tell you, so we measured an apartment complex that had 75 air source heat pumps. We had the power data for the apartments. We also had, there was resistance in the bathrooms. And we saw a diversity that was about a third of what you would have expected if you assumed all 75 heat pumps were on at the same time. So I just wanted to point out there might be a few things like diversity and thermal mass that might attenuate the difference, but geothermal is still clearly better.
Well, as we talked yesterday, Hugh, you know, most of the time we're thinking about single-family homes.
Yeah.
So there's not much of a diversity in a single-family home in heating, but certainly in multifamily you would have
Yeah.
more of that happening. Yeah.
Well, and traditionally for single family for cooling, we assume that there's 70% diversity, right? So, yeah, and you're right, there's not much good data on what the diversity is for single family yet.
All right, any questions?
Thank you. Henrich Carroll with Willdan Energy Solutions. Great presentation, Mr. Brown. We don't do a lot of residential, but definitely we do commercial. And the chart that showed the KW demand based off of the information you had there is excellent. Is there anything that when you look at a commercial establishment that gives you a KW calculation? Because utility bills for residential don't show KW, but when you get to commercial, they do show KW, and therefore we can calculate by seeing the KW difference for the customer how much they're going to save on the electric bill versus for the KW change.
Yeah, the commercially the equipment would be the same, but there would be this caveat, and that is I think you'd have more diversity in a commercial building because most commercial buildings, even up this far north, are going to be mostly be cooling. So you're talking about heating dominated, or you talking about cooling dominated?
For the customer we work with, I guess it would be cooling.
Yeah. So for cooling, the numbers probably are at least close, because that assumes that you're running pretty well full out. And I think that's, you know, on a hot day, that's probably what you would have in a commercial building. So you'd have to just get the right equipment in there, but essentially variable speed versus loop temperatures versus outdoor air temperatures, that ratio is probably not that much different.
Okay.
Of course, you could have a cooling tower, you could have other stuff with the water source unit. But as I said, this is based upon actually probably a high 70s loop temperature, which would be typical for Albany here in the summer.
All right. Thank you.
Well, okay.
Well, I think that's it. So thank you very much. Whoa,
The boss.
Do I have to take him for my boss?
For you, Bob.
So, you know, I think the interesting thing is there's no doubt that the cold climate air source heat pump has made significant progress with the technology advancements that Bob referenced. And this is trying to get a level set of, okay, where are we at after we implement those improvements? And when we talk about peak load impact to utilities, you know, 1,000 homes on GEO that are at this sub-zero temperature, you're going to save 10 megawatts of peak load impact for the utility, which is not negligible. That's somewhere between a third or a sixth of an incremental IC gas turbine that costs them $2,000 a kW for the initial cost to install it. So it's $20 million every 10 megawatts they got to put in. So my question is, does anybody in the audience, the whole purpose of what's happening here is to reduce Scope 1 emissions in buildings. So does anybody in the audience have any knowledge or insight on we're moving emissions on those cold winter days from a house or a building, and we're moving it back to the utility because the only option they really have for dispatchable power is an IC gas turbine that they can respond with dispatchable generation. Does anybody in the audience have any experience on what's the balance on emissions of a COP on site if you're replacing a fossil fuel device that would provide an incremental benefit to overall emissions versus the utility investing that $20 million for 10 megawatts and spinning an IC gas turbine that has its own Scope 2 emissions profile? Hugh or anybody else, does anybody have any experience that says, if I'm taking out a 97% AFUE gas furnace in a home and I'm going to put in a heat pump, the COP should be X at peak, or otherwise I'm just moving emissions. I'm not really changing it.
So
Anybody have any experience on that?
you're John, right?
I think so, yep.
I don't answer unless I know your name.
My name's
I'm
John Thomas, sir,
okay.
yes.
All right. So I deal with local law 97 in New York City, right? And to do what you're saying, so you can use either their standard emissions factor, or you can hire an engineer and pay them to do an analysis of the grid, and you can figure that out. But I don't have a strict answer just to say it goes up 1 or 2 points. Local Law 97 requires you hire an engineer and do the calculation over the hours of our run hours, basically. But you're right. There is what you're 100% right. That as the utility, if you're using a dirtier utility, you're going to have a different, right? You're going to have a different emissions factor, a higher emissions factor.
Well, I just want to clarify. I don't want to portray anything I'm saying that refers to a description of a dirty utility. The utilities only have one option for on-demand dispatchable power, and that's icy gas turbines. 14 to 16 minutes, they can flip the switch and turn 50 to 60 megawatts onto the grid to meet that spike demand when all this electric resistance backup heat kicks on.
And what I'm saying is that for the customer, for us, an institution, Pratt Institute, we have to use the emissions factor for the grid that they give us. If we can, we can. If we don't use that, we have to calculate what it should.
What I was pointing out, we're using the wrong matrix in terms of what we charge people for. Do we charge them per kilowatt demand, or do we charge them for the residential customer for a blended rate? And that's the problem, because a lot of people, they don't pay the price for their inefficient in their own system. They don't pay a price for putting a couple 10, 15 kW of additional capacity needs onto the grid, because it's blended and it's rate-based, and they only pay for a kilowatt hour, a blended rate for the whole month. So they don't pay the actual price for that. It's a problem. And they don't care, because they said, well, it's not going to cost me much, it's going to cost the grid. That's not me. So we need a different structure.
I haven't bought this all of the key operation.
Yeah, no, I understand that. Everything else we're going to talk this afternoon about.
Yeah, that's that.